Hi, this is the MOSOMIC MEMS Microphone Guide. My name is Mikko Suvanto. In this episode I continue talking about the electrical implementation of MEMS microphones into devices. I'll dive into electromagnetic and electrical compatibility of MEMS microphone implementations. I'll talk about RF immunity, conductive and radiated disturbances, and disturbance minimization. Stay tuned! This series is sponsored by Innovating Technologies. The electromagnetic compatibility, EMC, of a MEMS microphone describes how well the microphone works in the electrical and electromagnetic conditions that can be found in modern wirelessly connected devices. In other words, EMC indicates how well a microphone operates together with all the other systems in the device, as well as electromagnetic systems external to the device. On the one hand, good electromagnetic compatibility means that the microphones don't disturb the rest of the system. On the other hand, it means that the other systems inside or outside the device don't cause significant disturbances in the microphone. Electromagnetic compatibility of a MEMS microphone in a device is affected by three main factors: the microphone component itself, the implementation of the microphone into the device system, and the properties of the device, for example, the electrical and electromagnetic conditions that surround the microphone. Electromagnetic incompatibility can occur in at least three ways. The first is that the microphone disturbs the other systems in the device actively. A poorly designed digital microphone can emit disturbances that may affect, for example, an antenna that is located very close to the microphone. Luckily, this is a rare problem because any emissions from a microphone are likely to be very weak, so interference occurs only if the microphone happens to be located very close to the antenna in exactly the wrong spot. Also, the digital output line of the microphone can potentially couple to another signal. This is also easy to avoid if the system designer knows what he or she is doing. The second way an EMC problem can occur is that the microphone disturbs some other system in the device passively. Passively means here that the microphone disturbs the other system without emitting anything. A microphone, with its built-in Faraday cage, is a relatively large, grounded conductive object. It can passively cause reduction in antenna performance if it happens to be in the wrong spot in relation to the antenna. The third type of EMC problem is that some other system in the device disturbs the microphone. This is the most common electromagnetic compatibility problem related to MEMS microphones. The other system is typically an antenna, a switching amplifier, or some other component that emits high-frequency disturbances. I talked about the role of the microphone itself in avoiding disturbances in episode 9, in which I talked about the power supply disturbance rejection performance and immunity to radio frequency disturbances. Also, the implementation of a microphone into a device plays a big role in this. In episodes 17 and 18, I talked about general electrical implementation considerations related to analog and digital MEMS microphones and how they affect the electrical robustness of the system. Proper implementation is important especially in wirelessly connected devices that may contain more than half a dozen antennas as well as other components that can cause disturbances. In this episode, we'll talk more specifically about how the implementation of a microphone affects the electrical robustness and performance of a MEMS microphone system. EMC issues are often difficult and time-consuming to analyze and fix. They can result in several different negative effects for the device designer and manufacturer. Time and money spent on investigating and correcting the problem, unexpected design changes, development schedule delays, and dissatisfied customers if the devices with poor sound quality end up in the market. Therefore, electromagnetic compatibility must be taken very seriously from the very start of the device development. There are many disturbance sources in a device, especially in a wirelessly connected one. The disturbances can affect the microphone in at least 3 ways. The first is that radiated RF disturbances can reach the microphone directly as radiation. The second is that radiated RF disturbances reach the microphone by polluting a microphone signal line and entering the microphone on it. The third is that RF disturbances get galvanically conducted into the microphone or the microphone signal lines. There are many different paths for disturbances to find their way into the microphone signals. Air, in other words radiation that finds its way directly into the microphone package. The microphone output line, the supply voltage line, the ground lines, the left-right selection line in digital microphones that is connected to the ground or to the supply voltage line, or the clock line in digital microphones. Conductive disturbances are disturbances that get into the microphone via galvanic conduction on an electrical connector. A common source for conductive disturbances is radiated disturbances that get coupled into one of the traces that go in or out of the microphone. The source of the radiation can be the antenna systems in the device itself or an external source. Another source type for conductive disturbances are other electrical components in the device. For example, RF systems, switching power systems, switching regulators, data buses, clocks, and components with sharp transients can inject high-frequency disturbances into signal lines. Disturbances can also get coupled to the microphone traces from other traces if the lines are located parallel and/or too close to each other. Another way for disturbances to get conducted into the microphone is ground. This can happen when microphones share the ground with other components and systems. It's also possible that radiated signals pollute a poorly designed ground. I talked about ground design in more detail in episode 17. Radiated RF disturbances can get into the microphone directly via air, or they can get coupled to the signal lines of the microphone. Especially in wirelessly connected devices that rely on cellular networks, such as smartphones, the radiated signal levels can be high. The antennas produce electrical and magnetic fields at very high frequencies. In wirelessly connected devices, the transmissions can be based on, for example, the TDMA, dynamic TDMA, CDMA, TDD, or some other channel access and time slot sharing system. The radio transmissions happen, for example, at frequency bands from 800 MHz to 900 MHz or from 1800 MHz to 1900 MHz. As technologies advance, higher frequencies are taken into use. The transmission power can be substantial, 2 watts or more, and the associated current can exceed 1 ampere. The transmission can become audible, for example, if there is a low-frequency repetition involved. This is the case with TDMA systems, where the transmission pulses at 217 Hz, resulting in a buzz at audible frequencies. It sounds like this. The RF transmissions can couple to the microphone output signal, or they can couple to the traces going into the microphone and enter the microphone as conductive disturbances. If the microphone is not properly shielded with a Faraday cage, the radiated signals can also penetrate directly into the microphone. The signals that enter the microphone can couple to the weak analog signals inside the microphone. They can also get demodulated into an audible disturbance in the microphone ASIC. Even though the RF immunities of MEMS microphones can be very good, it's still necessary to minimize the disturbances also on the system level. Coming up with a MEMS microphone implementation into a device that helps minimize disturbances boils down to a handful of key things: component selection, circuit design, schematic, circuit layout, component placement, microphone in relation to noise sources, grounding, filtering, and shielding. Radiated disturbances should be minimized by placing the radiated disturbance sources, such as antennas, as far as possible from microphones and the microphone signal traces. RF designers should be consulted when the device design and circuit board layouts are being finalized to make sure that microphones are not located at especially bad locations when it comes to electromagnetic fields emitted by antennas. Also, the amount of disturbances on the traces going in and out of microphones should be minimized. For example, filtering should be used to remove RF content from the signal lines. I'll talk about filtering in more detail in a minute. The microphone traces should also be shielded from disturbances when necessary. Good grounding is a critical factor in the electrical implementation of a MEMS microphone into a device. Good grounding provides disturbances a low impedance path to the device ground, making sure that the disturbances bypass the microphone and its sensitive signals. Poor grounding increases the risk of RF disturbances, signal crosstalk from other traces, and higher system noise level. Indications of poor grounding are, for example, variations in ground potential from one point to another in the ground, as well as disturbance currents in the ground. Poor ground quality can be caused by, for example, too narrow traces, inadequate amount of bias between the ground layers of a circuit board, or a flexible circuit board with narrow and/or long traces, high trace impedances, or low-quality connectors. Poor grounding can also be caused by different subsystems located in a device so that sensitive signals, for example microphone return currents, get mixed with disturbing signals such as digital return currents. Shared grounds are a common way for disturbances to propagate from one part of the system to another. Microphones should not share grounds with systems that are prone to cause disturbances, like pulsing return currents. Also, digital and analog systems in a device should be separated to avoid disturbances. Well-designed ground traces and ground planes help keep disturbance propagation to a minimum. Like I mentioned in episode 17, the star grounding system can be used in the device to help separate microphone return currents from other currents. This also helps minimize voltage differences between the ground at the microphone and the ground at the system that receives the microphone output signal. If possible, the ground plane should cover the whole circuit board so that it provides a low impedance path for all return currents. This minimizes disturbances and voltage variation in the ground plane. There should at least be a solid ground plane under the microphone and its circuitry. The ground should not be divided into two or more sections by traces running on the same circuit board layer. Also, filling all free circuit board area with ground planes helps minimize ground impedance and reduce capacitive coupling of high-frequency disturbances from other signal traces to the microphone lines. Acceptable trace lengths are typically shorter for analog signals than for digital signals. Vulnerable analog signal traces between components must be kept as short as possible by placing the microphone and other components close to each other. The longer the trace is, the more efficiently it can act as an antenna that can pick up disturbances. Especially the connections from the microphone ground pads to the ground plane of the device should be as short as possible. If possible, the connection to the ground plane should be done with a via directly from the pad the microphone ground is soldered on. Just like with the connections from filtering capacitors to the power source, traces in the XY plane of the device circuit board should be avoided. Sometimes short traces are not possible. If the microphone output line is long, a digital interface should be considered. To avoid signal coupling, microphone traces should not be placed close or parallel to other noisy traces. For example, RF signals and traces carrying high-power dynamic currents can be noisy. The return currents of these systems can cause also the ground to be noisy. Also, noisy traces with RF currents or dynamic currents should not be routed under the microphone. Crosstalk can happen also between two microphone signal lines. If microphone traces must be crossed with noisy signal lines, the crossing should be done perpendicularly to minimize coupling. Even though digital signals are robust against disturbances, it's still a good practice to keep the microphone clock and data lines physically separated from potential disturbance sources such as RF systems and high-speed transmission lines. Like I explained in episode 17, the microphone signals should be shielded from radiation and other coupling with a Faraday cage. The cage should start in the microphone package and extend all the way to the system that receives the microphone output signal. Let's have a look at a principal example of a Faraday cage extended to the device circuit board. Here we have an analog output top port microphone seen from the bottom side. The microphone package has a built-in Faraday cage. As you can see, there's a ground ring that circles on the bottom edge of the component. In this example, there are two signal lines to be routed out of the microphone. Here are the signal lines connected to the contact pads the microphone is soldered on. Here I added the device circuit board within which the signals run. Here's a ground layer that lies between the microphone and the signal lines. Now I add a multitude of vias between the ground ring on the device circuit board that the microphone is soldered on and the device ground layer to connect the Faraday cage in the microphone to the ground plane in the circuit board. Here's another ground layer, this one on the other side of the signal lines. Now the signals are sandwiched between the two ground layers. The icing on the cake is the via stitching between the two ground planes on both sides of the microphone signals, creating a full protective cage around the signals. A key performance enabler for Faraday cages or shields is good grounding. Special care should be taken to make sure that high power or high current systems in the device don't disturb the microphone. Traces carrying high power supply currents should be routed adjacent to a ground layer. For high power signals, it's also important to make sure that all parts of the electrical connection, traces, vias between layers and so on, are able to carry the current without becoming a bottleneck. Power amplifiers should be placed close to the device battery terminals to minimize ground impedance for the return currents. It's also important to minimize disturbances in the power supply line of the microphone. To achieve this, a low noise regulated power supply is recommended. Also, the whole device system layout should be designed to minimize disturbance coupling to the power supply lines. The microphone power supply should not be shared with systems that may introduce disturbances in it, such as RF systems or digital components. The power supply line should be kept away from disturbance sources and shielded from disturbances when necessary. In addition to that, the line must naturally be filtered properly. Disturbance filtering is a key method to minimize disturbances that could otherwise affect the microphone. The basic idea of filtering is to direct the disturbances to the ground of the device before they reach the microphone. In some cases, the goal may be to make the disturbances dissipate as heat. Separation of disturbances from wanted signals is typically done based on frequency. This is possible because the frequencies of audio signals below 20 kHz are typically significantly lower than the high-frequency disturbances that are to be filtered out of the microphone lines. The filters can be built into the microphone, or they can be a part of the microphone circuitry in the device. Filtering built into the microphone reduces component count and cost, and also saves space on the device circuit board and, if designed correctly, can be more efficient than filtering done outside of the microphone. The closer the filters are to the microphone, the better chances they typically have to effectively filter disturbances. The challenge with filtering built into the microphone is that it doesn't always perform well with the filtering that's done outside of the microphone. Tuning the filtering in the microphone to optimize the overall filtering performance typically takes more effort and time than optimizing filtering on the device circuit board. Filtering done outside of the microphone is typically done using discrete components such as capacitors, inductors or ferrites, so the filtering can be fine-tuned easily by changing component values. If the device manufacturer uses microphones interchangeably from multiple microphone suppliers, the filtering in all the microphones should be similar to avoid variation from one device unit to another. This may be challenging to accomplish in practice. There are different ways of including filtering in the microphone. First of all, discrete filtering components can be assembled onto the substrate board of the microphone. Another way is to build capacitors into the microphone substrate board by forming them out of adjacent conductor layers in the circuit board. Capacitors formed with this method tend to be less than ideal in terms of parasitic resistances and inductances, so their performance may be compromised. The more wiring, traces, bond wires, vias, and so on, and components there are in the microphone, the higher the risk of parasitic inductances is. Filtering can also be included into the ASIC of the microphone. Also, the properties of the component that receives the microphone output signal, for example a codec, should be taken into account when designing the filtering for the microphone signals. A typical filter is a capacitor that's placed between the filtered signal and ground. Capacitors act as bypasses for high-frequency disturbances on signal lines. A correctly chosen capacitor lets high-frequency disturbances through to the ground. Audio frequencies do not pass the filter capacitor, so they remain on the signal line as they should. The capacitance value of the capacitor determines which frequencies and disturbances it bypasses to the ground, so the value must be chosen carefully to maximize filtering performance. There should always be a filtering capacitor on the microphone supply voltage line to prevent disturbances. The values typically range from 10 picofarads up to 10 microfarads to cover all disturbance frequencies that might appear on the supply line. For example, 3 different value capacitors can be connected in parallel with each other. One bigger one, for example 0.1 microfarads or a little bit bigger, and a couple of smaller ones between 10 and 500 picofarads, depending on the frequencies that need to be filtered. For best performance, the smallest capacitance should be connected closest to the microphone. The circuit layout for the capacitors affects the efficiency of the filtering. Generally, for the best possible filtering results, the filtering should be done as close to the sensitive circuitry in the microphone as possible. Also, the lengths of the electrical connections from the power source to the capacitors should be minimized. Best practice is to avoid traces on the circuit board and use wires directly from the contact pads of the capacitors to the power plane. Also, trace inductances should be minimized to avoid any unwanted changes in the way the filters work. It's noteworthy that some capacitor types can cause audible noise. Therefore, they should be avoided close to microphones. This is, of course, contradictory to the rule that the filter should be as close to the microphone as possible. Noisy capacitors can be, for example, capacitors based on Class II dielectrics. The filter can also be an inductor. An inductor is placed in series with the signal line. Inductors present a high impedance to radio frequency signals, thereby blocking them from the signal line. Again, low frequencies, such as audio frequencies below 20 kHz, are not affected. Another filter type used for high-frequency disturbances is a ferrite bead. They are low-pass filters that suppress RF energy by converting it to heat. A series resistor on a trace, for example the power supply line, may also help minimize disturbances. There are also more complicated filters, such as the pi filter. It consists of 2 capacitors and an inductor, as you can see here. Well-designed pi filters are more effective than simple capacitors or inductors, so they should be used in more problematic cases, for example on long traces. A good starting point for the capacitance value is 33 picofarads. It can be varied based on how effectively the filter works. In the case that a microphone causes problems with antenna performance passively by being a grounded metal object in the wrong place, The best and often only cure is to move the microphone further from the antenna. Good grounding of the whole microphone package is also important. If a microphone disturbs an antenna by emitting disturbances, the microphone design and quality should be checked. The problem may be caused by poor grounding. This can be caused by either a bad microphone or bad grounding of the microphone in the device. The problem in the microphone that causes disturbance emissions can be, for example, bad signaling in the microphone. To be precise, too fast rise and/or fall times of digital signals. If the problem is in the microphone and it cannot be fixed, it's probably best to switch to another microphone model. If that's not possible, the microphone should be moved further from the antenna, or shielding could be put around the microphone. Okay, that's it for this episode. In episode 21, I'll talk about the microphone implementation in relation to electrostatic discharges, ESD. I hope I'll see you around. Cheers! If you have any comments or questions, write them down in the comments below and I'll do my best to answer them. You can also contact me online or on social media. If you like what you saw here, give a like for the video and subscribe to the MOSOMIC channel. That way you help me reach more people and thereby create more content. If you need more in-depth microphone training than what you saw here, contact me and we can arrange it. The training can be adapted to suit any interests and skill levels, and the customer can choose the location and duration of the course. MOSOMIC provides also consultation services in all things related to MEMS microphones. If you're a microphone buyer, I can help you select the right components for your product and manage your microphone suppliers. I can also assist in implementing the microphones into your device. For microphone manufacturers, I provide microphone marketing, product definition, product management, and development management services. I can also help you create all kinds of MEMS microphone documentation.